In section 1.4 of this intermediate algebra course, we are now going to be talking about solving linear equations. Now, earlier in this course I mentioned to you that algebra is all about finding the missing piece, finding the missing value. When there is a numerical relationship between quantities and a problem, very often we are trying to find some missing value and we know the rest of the information. Well, in this particular case, we're going to start doing that. We're going to look at the simplest types of equations that there are to solve. These are called linear equations. In fact, they're so important that as we look at more and more complicated equations, we're going to eventually look at polynomial equations. When you get to college algebra, you'll be looking at radical equations, rational equations, exponential and logarithm equations. Turns out, from this point on, after we've done section 1.4, our goal on every equation problem is to somehow reduce it back to a linear equation. Because if we can solve linear equations, that's like the keystone, the foundation for solving all of our algebra problems. Turns out it's not that hard. Really, all it is moving things around until you get the variable by itself, and I'll show you exactly how to do that in this section. The essential concepts that we will be covering in this section are as follows. We will start by solving linear equations. When we introduce linear equations, we'll see something come up that we have to address, and it's the difference between what are called identities, conditional equations, and inconsistent equations. Once we can solve equations and know the difference between those types of equations that we may have, we're going to solve problems using mathematical models. So solving linear equations in one variable, that's where we're going to start. A linear equation in one variable is an equation that can be written in the following form: ax plus b is equal to 0. Now, what makes it linear is there are no powers of x. Okay? No higher powers of x. There's no roots. I should say no powers greater than 1. There are no roots. X is not in a denominator. Those are some key aspects of things that make this linear, but most importantly is that you could eventually write it in this form. That's going to be called a linear equation. A and b are just real numbers, so in a particular problem it may be like, say, 4x minus 12. Okay? Now, to solve an equation means to find all the values of the unknown variable, in this case x, which satisfy the equation. So one way to ask a question, although this is not very common in practice, right? Really what you're going to be given is the equation and try to find the variable. But say, for example, I ask you, is this particular value of x a solution? Does x equal 3 solve this? Does it satisfy it? And what you do is you check, right? You plug it in. Say 4 times 3 minus 12. Is that equal to, and I'll put a question mark over the equal sign to say we don't know yet. Does that equal 0? Well, clearly 4 times 3 is 12, right? 12 minus 12 does equal 0, so yes, it is. It satisfies the equation because when I plug it in, the equation is true. Right? 12 minus 12, or 0, equals 0. It's true. So that's what we mean by a solution. Now, how do I go from this to x equals 3 is the question. Well, to solve them, we're going to use properties of equality. So basically, say for example, we've got the following equations, right? We've got x minus 3 is equal to 8. There is something called the addition property of equality, which means we can add something to both sides or subtract something from both sides, or add a negative, and it's still true, right? It doesn't change the truth value of the equation. So I'm going to take advantage of that fact and say, well, okay, if I have x plus 3 and I want x by itself, I can do the opposite of subtracting 3 and add 3. Right? But if I add 3 to one side, I'm going to add it to both sides so that the truth value of the equation doesn't change. Meaning the solution set of that equation. Doesn't change. So if I start with x minus 3 and that equals 8, and I add to both sides 3, notice what happens. The minus 3 and the plus 3 become 0, right? And you end up with just x on the left-hand side and 11 on the right-hand side. So x equals 11. Clearly, 11 satisfies the original equation, so that's the solution. The solution set is 11. I use curly braces because when we talk about sets, right, generally we use curly braces, but all I'm saying is that the solution to this equation is 11. And I got there by doing the opposite. Now what about the opposite of adding 7? If I have x plus 7 and a negative 15, what can I do to do the opposite? I can subtract 7 from both sides, right? And what happens when I do that? What is x plus 7 minus 7? Well, that's just x. Right? And what's negative 7 minus 15, or minus 15 minus 7 is negative 22. So the solution set is negative 22. All right. Now, what about division or multiplication? The connection between those. Well, if I have 6x equals 30, I can divide both sides by 6. Right? And what happens is the 6's will cancel here. So I end up with just x equals 30 divided by 6, which is 5. So the solution set is 5. 5 is the solution to that equation. And I get there by just taking that 6 off. And here's how you remember that. You ask yourself, how is the number connected to the variable? Right? If it's connected by multiplication, you do the opposite. You divide. If it's connected by addition, you subtract. If it's connected by subtraction, you add. Right? If it's connected by division, so we have x over 5 and 9. How am I going to get the 5 off? I'm going to multiply by 5. Right? And so the 5's here, 5 divided by 5 cancel. I'm left with just x on the left-hand side, and on the right-hand side 45. So the solution of that is 45. That's how we use the properties of equality. The addition property of equality and the multiplication property of equality. Using those principles, those properties, we can lay out a set of steps that we're going to use to solve every linear equation from this point on. First, and I put this in parentheses because you won't always have to do this, but clear fractions if necessary. If you've got fractions in the problem, there's a trick to get rid of those fractions completely. It's called multiplying through by the LCD. Right? LCD stands for lowest common denominator, which we've used that, right? Common denominators are used for adding fractions together. Well, if you can find a common denominator, you can also multiply both sides of the equation by the common denominator using the multiplication property of equality. Doesn't change your solution. So do that, and that happens to cancel every denominator in the problem, which is fantastic, right? Because that means we don't have to worry about fractions in our steps for solving equations. All right, so begin with, after you've gotten rid of fractions, you don't have to worry about them, you simplify the algebraic expression on each side. Just simplify both sides as much as possible. Then you collect all the variables on one side and all the numbers and constant terms on the other side, or constant terms on the other side. Then you isolate that variable, meaning you get its coefficient off of it, and it's solved, right? And then at that point you check your proposed solution. That's the beauty of solving equations. Finding the missing pieces, you can always plug it back into your equation to see if you're correct. So let's solve and check, say, this one according to those steps. All right, step 1. There are no fractions, so I'm not going to worry about that procedure. But I can simplify each side, right? I can collect like terms. On the left-hand side, I have a 2x and an x, so that becomes 3x minus 12. And on the right-hand side, I can also simplify by combining the 6x and the 5x to 11x minus 4. at which point both sides are as simplified as they can be. Now I'm going to collect all the variables on one side. So let's say we subtract 11x from both sides. All right, that's going to move that 11x to the left-hand side and get that variable over there. Follow? Because on this side they subtract out. 11x minus 11x is 0. So I have on this side negative 8x minus 12 is equal to negative 4. Now move the 12 to the other side. So add 12 to both sides. Okay, over here they subtract out. That negative 12 plus 12 is 0. So I have negative 8x equals negative 4 plus 12 is positive 8. Now I have finished step 2 by collecting all the variables on one side and all the numbers on the other. So now for step 3, I'm going to isolate that variable by dividing both sides here by the negative 8 that's connected to it. Okay, so the negative 8's divide out. I have x is equal to 8 divided by negative 8. 8 divided by 8 is 1. You take the, since it's opposite signs, you're going to take the negative along with it. So that's negative 1. Now, check. Okay, is that the actual solution? How do I check? I plug it back into the original equation and see if it's actually true. Right? I plug in 4x and negative 1. So notice on the left-hand side, all I'm doing is putting a negative 1 where there's an x. Put a question mark over the equal sign. Is that equal to 6 times negative 1 minus 4 plus 5 times negative 1? So 2 times negative 1 is negative 2. Use order of operations to simplify these things. 12 minus 1. On this side, 6 times negative 1 is going to be negative 6 minus 4 minus 5. So over here I get negative 15. Over here I get negative 15. Those are equal, so it checks. Which means we've got the right answer. X is equal to negative 1. Okay, so once you've checked, then you can put a box around your answer and say that you're done. Alright, let's do another one. Again, I'm going to go through my steps for solving this particular equation. The equation we're asked to solve here is 2 times the quantity x minus 3, all minus 17, is equal to 13 minus the quantity 3 times x plus 2. Okay? Let's do it. Step 1, simplify both sides, which means on the left-hand side we need to multiply things out. So distribute the 2. So I end up with 2x. 2 times minus 3 is minus 6. Minus 17 equals, and then on the right-hand side I'm also going to distribute to multiply this out. So I have 13 minus 3x. A minus 3 times 2 is minus 6. Be sure you keep track of those signs. I can simplify both sides still by collecting like terms. So 2x minus 23 is equal to 13 and 6. I can do 7 minus 3x. Alright, now let's get the x's on one side. So let's say we're going to move the 3x to the right hand side. I can do that by adding 3x to both sides. Gives me 5x minus 23 is equal to 7. I can now move the 23 to the right hand side by adding it to both sides. So 5x is equal to 30. Now for step 3, let's get that variable by itself. So divide both sides by 5. 5 cancels out here. I have x is equal to 6. So let's check our answer. So that's 2 times 6 minus 3 minus 17. Is that equal to 13 minus 3 times 6 plus 2? So inside the parentheses on the first step, and the left hand side gives me 2 times 3 minus 17. Is that equal to, and I can add the parentheses on this side, so 13 minus 3 times 8. Now multiply. I have 6 minus 17. Is that equal to 13 minus 24? 6 minus 17 is a negative 11. 13 minus 24 is a negative 11. They are equal. It checks. So that is the correct answer. Alright, on all these checking, the main reason you check is to make sure that you did it correctly. It's not possible that you would have done all the steps correctly and then it doesn't check out. For linear equations, that's not possible. Okay, so if this is not true over here, either you made a mistake in checking or you made a mistake in deriving the solution, so you want to check your work in both places. Now let me show you an example where you can use that little trick that I mentioned before of getting rid of the fractions. Right? Notice in this particular case we have fractions throughout the problem, and while we could do the work with the fractions in there, it's preferable to get rid of them so that we can work with simpler forms. And since there is a technique that does that, let's take advantage of that. In this case, the LCD will be the LCD of 5, 2, and 2. You look at all the denominators in the equation and find the smallest number that they all divide into, right? The smallest multiple of any of these numbers that every other number also has as a multiple. So 10 is the smallest number in this case that they all go into. So what I'm going to do is multiply everything here by 10. I'm going to take 10 times 2x plus 5 over 5 plus 10 times x minus 7 over 2 equals 10 times 3x plus 1 over 2. Basically, I multiplied both sides here by 10, multiplied by 10 here, multiplied by 10 here. On the left-hand side, because it's a plus, I distribute it. Okay? So that's what happened there. So 10 times 2x plus 5 over 5. That's 10 divided by 5 will cancel out and leave me a 2 times this whole expression. So 2 times 2x plus 5 is left from the first term. 10 divided by 2, right, goes in there. 2 goes in there 5 times. So I have plus 5 times x minus 7. And then 10 over here also divides out. Both have a 2 as a factor, so I'm left with 5 times 3x plus 1. Now here's the beauty. Look, no fractions. Woohoo. I say woohoo. Now we can go through our steps one by one. So I begin by simplifying each side. That means I'm going to need to multiply out the left-hand side. 2 times 2x plus 5 gives me 4x plus 10. 5 times x minus 7 is going to give me a 5x minus 35. On the right-hand side, 5 times 3x is 15x, and 5 times plus 1 is plus 5. Still simplifying, that's still step 1. I can combine like terms on the left-hand side and have 9x minus 25, I believe, right? 10 minus 35 is a minus 25 equals 15x plus 5. Now, I'm gonna start pushing you ahead a little bit here. Let's do both steps in one. Let's move the 15x to the other side and the 25 to that side. So I'm gonna do 2 steps in one. I'm gonna subtract 15x from both sides, line them up, and I'm gonna add 25 to both sides. Right? I can do in 2 steps what I used to do in one. 9 minus 15 is negative 6x. 25 subtract out. The x's come to subtract out. So that equals 30. Right? Negative 6x equals 30. Just by moving things around. Now divide both sides by negative 6. Okay, double arrow means implies, so that implies that x is equal to negative 5. Now, you can go ahead and check. If I told you that checking is to make sure you did it correctly, you can trust me. At least I've checked my work. That is correct. When you're doing this on your own, you'll definitely want to check your own work. Okay? So our final answer is x is equal to negative 5. If you take this value here and substitute it back in up here to the original equation, you will see that it does in fact satisfy. Now I want to take a look at a couple of other equations that throw us a curveball, if you will. They surprise us with something that happens. As you go through the steps to solve these, the same way that we've gone through the steps before, you see that you have 4x minus 7 is equal to 4x minus 4 plus 3, or 4x minus 7 is equal to 4x minus 1. Okay? Just by combining like terms. I distributed the 4 and then I combined the like terms, so both sides are now simplified. Now let's begin by moving the x's around. I'm going to subtract this 4x from both sides to move it over, and uh-oh, you have something happen that hasn't happened before. The x's are gone. How can I get x by itself if they drop out completely? Well, if they drop out completely, that means we have a new type of equation that we have to deal with. Look at this statement. You have negative 7 is equal to negative 1. As a result of properties of equality, techniques that we know don't change the truth value of the equation. They don't change the solution set. Now, look at this. Is negative 7 equal to negative 1? No, that's false. Which means no matter what x we started with, it's always going to be false. So if that happens, if the x's drop out and the resulting equation is a false statement, that means there is no solution. And that's what you write your answer as, no solution. In fact, in the computer, you're going to just type in capital N. And it tells you that in the instructions. If there's no solution, type a capital N. Now, these types of equations are called inconsistent equations, right? If they don't have a solution, that means they are inconsistent. Okay, now what if the same thing happened, things drop out, but you end up with a true statement? Like, look at this one. 4x plus 6 is equal to, now simplifying the right-hand side, I end up with 6x plus 6 minus 2x. Simplifying the right-hand side, you have 4x plus 6 is equal to 4x plus 6. Already you got a clue, right? Those things are identical, but say you go one step further. The x's drop out, you have 6 is equal to 6. Right? Well, clearly that's true, and every step I took to get to this point meant that that statement stayed true, which says that no matter what x you plug in here, no matter what x you plug in, you always have a true statement. That means every x is a solution. The solution set is all real numbers. Every number is a solution, but that's how you type that in. Okay? Okay, the real numbers are the solutions. Now that type of equation is called an identity, and I think you can see why, right? Because you get to a place where it's identical, right? Those are called identities, when every value of x satisfies the equation. Okay? All other equations, I'll write this down here in blue, note, all other equations, meaning equations that aren't inconsistent and aren't identities, are called conditional equations. Okay? Alright, so you'll need to be able to differentiate between identities, inconsistent equations, and what are called conditional equations. Inconsistent, if it has no solution, it's an identity. If all solutions are possible, that is, every number is a solution, all real numbers. And otherwise, when you get one answer, you're getting a conditional equation. Let's do one last problem, a problem where we're asked to use a mathematical model and solving equations to answer a question. In this particular case, we are given that this formula, t equals 857x plus 12,127, models the average cost of tuition and fees at private U.S. colleges for the year ending in X years after 1996. Okay? So X is the number of years after 1996. T is the average cost of tuition at private U.S. colleges. The question is, when does the tuition and fees reach 21,554? All right, so we have an equation with two variables. We have one value of the variable. Now, which variable do we know? Do we know tuition and fees, or do we know X years after 1996? And the answer is we know tuition and fees. So this number is going to plug in for T, right? That is the value for T. So plug it in and see what you get. Plug in this for T. 21,554 is equal to 857x plus 12,127. You have a linear equation in one variable. So to find the value of x that makes that true, solve the equation. So subtract 12,127 from both sides. And it's okay if the x ends up by itself on the right-hand side because it doesn't matter which order the equation is in. 21,554, I'm going to plug this in my calculator and subtract that. I end up with subtracting 12,127, 9,427 is equal to 857x, and these cancel. Now I'm going to divide both sides by 857. Again, going to my calculator to do this division problem gives me 11. So x is equal to 11. Now don't circle that answer because you're on a word problem. On a word problem, you always need to answer the question. And just because you get a value for a variable doesn't mean that that's the answer to the question. 11 is not the answer because the question is, when will the tuition and fees average that? 11 doesn't tell me the answer, but we can interpret that, right? X is years after 1996, so 11 years after 1996 is 2007. So in 2007 is the answer. That's when the tuition and fees will average 21,554. Actually, technically at the end, or the year ending in 2007. Okay? And that is the end of section 1.4.